We'll start with the idea of the limit, which is just the idea that we can get infinitely close to a point without ever actually reaching that point. This idea of infinitely small or infinitely thin is the foundation for all of calculus. Just imagine two hikers approaching each other on a hiking trail. They might start miles apart from each other, but eventually they'll meet at some point along the trail. Over time, they get so close to each other that they're eventually nose to nose. Technically, they could continue to get closer to each other without ever actually touching each other by always cutting the distance between them in half. That's the idea of a limit, that we can get closer and closer to a point, in fact, infinitely closer, without actually arriving at that point. If we model the hiking trail with the function f of x, and our hikers are approaching a point called a, then we say that L is the limit of f of x as x approaches a. This notation tells us that we're trying to find the elevation of the hiking trail by using the elevation of the hikers. The closer the hikers get to A, the better idea we'll have of the elevation of the hiking trail, and limits tell us that they can get infinitely close to A, which means we'll be able to infer exactly what's happening at x equals A. After limits, we'll tackle derivatives, which use the idea of the limit to calculate instantaneous rate of change, which is really the central question of Calculus 1. We know from algebra that rate of change is just the slope of a function, and we know how to use 2 points on a line to find the slope of the line. But now we want to be able to find the slope of curved functions, not just lines. How do we do this? Well, we use 2 points on the function, just like we did in algebra with a linear function. But then we use the idea of a limit to bring those points infinitely close together. The closer we bring the points together, the more accurate our approximation will be of the slope of the function in between them, even though the graph of the function is curved. In other words, once we understand the idea of a limit, we can use it to calculate the derivative, which is just the rate of change or slope. We'll learn how to work with any function f of x to find its derivative, f prime of x, which we find with this formula, and which we know will be a new function that models the slope of f of x everywhere. Notice the limit notation in the definition of the derivative. Then we'll look at how to evaluate f prime of x at a particular point to find the slope of the original function there. Finally, we'll look at applications of derivatives, where we'll apply derivatives to different real-world problems. The idea here is that if we can know the slope of a function by finding the derivative, then we can use it to figure out maximum and minimum points along the function. In the real world, this means we're trying to optimize whatever the function is representing. Maybe a company wants to minimize its costs or maximize its profits, or maybe a farmer is trying to maximize crop yield or minimize pesticide use. To find these critical points, we'll use the first and second derivative tests, which involve finding points where the derivative is 0, and then checking the sign of the derivative around those points. So for the company wanting to minimize the cost of producing their product, the cost function might be a function of the number of units produced, and it might include factors like labor, materials, and overhead costs. By taking the derivative of the cost function with respect to the number of units produced, we can find the rate at which the cost is changing. Then, wherever the derivative is negative, the company knows that increasing the number of units produced will decrease the cost. But wherever the derivative is positive, they know that increasing the number of units produced will increase the cost. And by finding any critical points where the derivative is 0, they can determine the optimal number of units to produce that will minimize their cost.